In this short presentation, I will talk about a work where we studied via molecular dynamics simulation the Pore translocation of viral RNAs. First of all, I will do a brief introduction on the single molecule manipulation techniques, such as mechanical stretching experiments, microfluidic devices, or Pore translocation. These techniques are very useful to probe the free energy landscape of molecules with a secondary or tertiary structure that is caused by the presence of non-covalent bonds. As a very simple example, one can consider the study of a worm-like polymer chain under stretching. In the worm-like chain model, the polymer is treated as a continuously flexible rod. This is a good model for semi-flexible polymers, such as a short strand of DNA. In this setup, as you can see from the pictures, an external force is applied to the ends of the chain, and the consequent extension is measured. As is shown in this classical work by Marco, the model is able to predict accurately the relation between the applied force and the elongation of the molecule. Things, of course, become a bit more complicated in the presence of a secondary or tertiary structure, as can be seen, for instance, in a DNA unzipping experiment, where a force is applied to the ends of a single DNA filament, which forms an hairpin. In order to stretch the molecule, one has to unzip the hairpin, breaking the bonds between the bases. This process can be modeled as an activated process with an energy barrier E with delta. Experiments of this kind are often performed with a ramped force protocol, where the force is increased linearly in time with a certain ramping rate. And the measures are repeated several times in order to measure the average rupture force. All this quantity can be related via the Belevan expression that you can see here on the slide. And in this way, knowing F and the ramping rate R, one can extract with a fit the value of E and delta, which characterize the activated process. Another system where this can be useful is the study of the translocation of molecules through a pore. In this case, is the small diameter of the pore, which requires the unfolding of the molecule to allow the translocation. And for instance, small RNA molecules are ideal for this system because they present a complex geometric structure with hairpins and pseudonauts. And moreover, this has a biological relevance because the translocation through the pore can mimic the interaction of the polymer with the lumen of the enzyme. So what we did, we chose to study the translocation of a short RNA module found in the genome of some flaviviruses, like the Zika virus, which has the remarkable property of resisting degradation by exonucleases while being easily processable by other enzymes. These exonucleases-resistant RNAs, as they are called, can withstand degradation by a broad spectrum of different exonucleases. And this is interesting because it suggests that this ability is not due to the chemical detail of the interaction between the RNA and the enzymes, but rather to some more general physical properties, such as the RNA's secondary or tertiary structure. Moreover, this effect is directional, meaning that the exonucleases, which are not able to process the RNA, try to start processing it from the 5' end, while other enzymes, which instead can process it, starts from the 3' end of the RNA molecule. So what we did, we modeled the enzymatic processing of the RNAs as a translocation through a cylindrical pore. Here you can see the three-dimensional representation of the RNA molecule, which is 71 nucleotide long. And on the right, you can see all the secondary structure, the helices, the pseudonauts of the RNA. We performed atomistic simulation using SMOG, which is a native-centric and implicit solvent models that is then able to reproduce the native conformation of the molecule. And here you can see the references to the two works I'm talking about. So what we found, well, first of all, we studied the translocation activation time, so the time that is required to start the translocation after we start pulling the RNA with a certain force. First of all, we tried with the linearly ramped forces that, which increase linearly in time. And we observe a dramatic directional effect. The onset of translocation for the 5' entries required much larger forces than the 3' entries. As you can see here in this histogram, this is the distribution of the time required to activate the translocation from the 3' ends, and they are much lower than the time required to activate the process from the 5' ends. And this is, of course, in agreement with the RNAs resistant to the exonucleases, as I said before. Moreover, because our model is native-centric and because the enzyme has not chemical details, is just a repulsive wall, we can also conclude that it's the xRNA, it's the RNA architecture that's relevant to this difference and to the degradation resistance rather than some chemical interactions. From the Belev analysis, using the formula I showed before, we can estimate the energy barrier of this process and the width, and these are the results. And as you can see, of course, the energy difference is higher for the 5' end, and the barrier is larger. This effect does not depend on the protocol, so other than the linearly ramped force, we also tried with constant and the periodic forces, and here you can see the results with constant forces. We can verify that the time required to activate the translocation follows an Arrhenius law for both the ends, so the time is proportional to the exponential of the applied force. And one can use the data to fit the value of delta, the parameter that is here. And the bigger is delta, the steeper this dependence is. And as you can see from the data down here, delta is larger for the 5' ends. And this means that the activation time grows more rapidly with decreasing the force for the 5' ends than for the 3'. And this explains the huge difference that we see for the enzymatic processing. The enzymes applies a quite low force on the scale of this graph, and so there's a huge difference between the activation time from the two ends. We can also see that these values are in good agreement with the one we find before with the Belev analysis. Other than the translocation activation time, we also measured the translocation duration. So once the translocation is initiated, how long does it take for the whole RNAs to pass through the pore? The duration of the translocation process is shown here in the figure and is approximately proportional to the inverse of the driving force. Also, if we can see that there are two different regimes with different slope, and they are more or less separated corresponding in correspondence to an inverse force of 0.7, 0.75. We can also see that the two branches of the graph for the two pulling direction, blue and red, they lie more or less on the common curve. However, after activation, we can see that the translocation does not proceed smoothly, but instead there are pauses and slowing down, and they of course correspond to specific region of the RNAs that are marked by arrows here in the picture that's shown the translocated fraction as a function of time after the activation of the process. There are these slowing down, and they are different when we are pulling from the 3' or from the 5' ends. In order to relate to this slowing down with the secondary motif of the RNA, we performed a waiting time analysis. So the waiting time is the time that each nucleotide of the molecule requires to go to the pore. These waiting time are shown in these two graphs here for the two different pulling direction, from the 5' on the left and for the 3' ends on the right. The peaks denote the largest contribution to the duration of the translocation process. And one can note that the peaks are localized in correspondence of specific secondary and tertiary elements. So, for instance, this time here is spent to unzip the P3 helices, and these two peaks here corresponds, for instance, to some pseudonode, the pseudonode 5, or to the helices P3, and these these histograms are different from the two ends because the different secondary motifs are encountered in a different order from one end and from the other. To our knowledge, this is the first time that the interplay of translocation directionality and the architecture of the RNA molecule are investigated with microscopic detail. These results provide verifiable prediction for future translocation experiments. Thank you very much.